Thank you. It's a super honor to be here. It was an incredible honor to have Avi. I never really thought I was his advisor, but I guess I am an official, so I'll take the credit. I think I've learned much more. We were talking last night at dinner, though. I do think that once a year it should be Advisor Day. And everyone has to wear a badge, and it has the name of their advisor, because I can't tell you, and maybe even your children's, children, your grandchildren, because I can't tell you how many times, not with Avi perhaps, he's so well known, but with other people that are very good, and I'll have a conversation and someone say, wait, you were their advisor? I'm not quite sure what that means. Okay, so I'd like to do, I wish I could do a whole 45 minutes of jokes and, I don't know, jokes, stories. But I definitely want to say some things about Avi. I think, I will do some technical things, but we'll keep it fun. This is a very fuzzy picture of you. I think I've seen in so many talks and so many interesting starts, I've done a lot of strange things to start a talk. I'm not going to try to fool you with this, but my plan when I've done stuff like this would be to say, where's the focus button? And start messing around and eventually get it right. And I remember at least once or twice someone who invited me to give the talk was getting nervous that some crazy person had showed up and was trying to adjust the projector. I also have at least once put things upside down to start and was trying to flip the cable. We'll be doing some of that. Anyway, Avi's birthday was the 9th, right? Right. So we wish him very well, and I hope to be here for another one of these wonderful events for him. So I wanted to say a couple of things. One, when he was at Princeton, and I was, here as an advisor, we ran a seminar, which I think I really have done. I think it's one of the most fun things we do. I've done it. I did it here many years, on and off, and we did the same thing for a while at Georgia Tech, where I am now. And I'm not a big person on puzzles, especially for graduate students, but we tried in this problem seminar to mix problems that, were probably doable, maybe, with problems that were impossible, probably, and expose people with lots of questions. And, one of the things, we all know, Erdős is famous for, I don't know how many, zillion papers that he wrote in his career. But one of the things I think Graham once told me, if you're going to write a lot of papers, you got to think about a lot of problems. You're not going to solve them all, but you have to really focus in on real problems. So one of the problems one day was, if I had a graph, is it three-colorable? And this, is a very basic question. At the time, you probably all know the answer, or at least many of you, or maybe all of you. But at the time, a couple of us had noticed a terribly embarrassing, stupid answer that you could do better than n colors. So you have a graph that's three-colorable. You could break it into blocks, and each block you could brute force search it, and therefore get yourself down to n over log n colors, because if a block was size log n, you had plenty of time to search the coloring, and you could use n over log n different colors. So I mentioned this to Avi, and then the next morning, I guess in the afternoon, the next morning he walks in, and he says, I think I can improve it. And I believe, I'm not sure this is actually, was this your first result? I think it was your first probably StockFox type result. And he said, I have a small improvement to, a huge improvement, of course, to root n. And I was, wow, I thought, well, this is really neat. How does it go? Is it really complicated? Whatever. Probably everybody, you all know this result. I mean, I'm not going to give it, I'm just going to give you a picture, but I thought it was a very good example of the way he thought even then, and I think one of the things that you see in so many of his papers, that he has long papers, he has short papers, he has some results that I think you could write down very quickly and prove quickly that are tremendously important, and the more complicated ones that require, long proofs. But I love the ones that, there's some blinding, brilliant insight that he had. And here, this has been improved. I think we're down below a half, right, to what, 3/8 or even perhaps better than that. I think, is that about right? 0.2, oh, I'm sorry. And we know it can't get to below epsilon because of beliefs about P and NP. And,
we just know that it can be 6, cannot be 3.
Oh, it could be. Okay, so.
5 is out.
Okay, then I'm mistaken. But Rudin was a big improvement. Thank you. And Avi noticed the following, which we all had missed. And he said, well, look, if there is a vertex with high degree, because its neighbors must be two colorable. Because the middle, say, is red, P1 is red, so you cannot require too many colors on your neighbors, so you just do that. And you kind of remove it into a recursion. And that works if you have high degree. But if you have low degree, and of course this can all be made quantitative, then you use Brooks's theorem, which basically says that you can color such graphs, it's degree +1, but in worst case, but you basically can color with the number of colors globally. And he not only knew Brooks's theorem, the famous theorem graph theory, but also knew the proof of that is constructive. So it is a real algorithm. So, so what does high mean and what is low? It's one of these very simple balancing. It's Rudin is roughly the right answer for this simple approach. And I just thought this was really great. And I was probably ticked off also because, I hadn't seen this or no one else had. But it was a very cool result, very cool. So anyway, that's one thing I wanted to share with you. You probably know it, but maybe say something about his oral exam. So at Princeton, he passed. Just want you to know. What we did is we had written exams, and then like on the Friday, the faculty got together and kind of graded the exams, and at the same time decided who passed and who failed. I mean, that's just the way it worked. But students were brought in. And we were a pretty small place. There weren't too many students back in the early 80s. But they were brought in to orally defend themselves. And typically, like, we might ask questions about a problem they made a mistake on, or maybe a problem they got right, but there was a deeper follow-up question, we could probe. And I thought that was I thought it was a nice system. We had some students who would come in and say, oh, I know what you want, and start rattling off the proof to the theorem they got wrong. And we, of course, being faculty can be difficult, would immediately say, no, we're not interested in that, and move somewhere else. But with Avi, of course, he had gotten them all right, and we started to ask questions, and it got, I won't say out of control, maybe your memory is a little different than mine, but it was follow-up questions, and then it started to get like, well, suppose you have this function, and it looks like the zeta function, and could you identify where the zeros would be, and Avi would go, I haven't thought about that, but here's an idea, and I'm slightly exaggerating, but I'm taking notes, this could be pretty good. Now, here's a quote. I believe this is a quote. And I'm not saying Avi is von Neumann, and I'm certainly not saying anyone in the room was Hilbert. But I believe the following is a quote I've looked up. And I've heard when it once said at von Neumann's oral, I guess Hilbert was in the room. Was he the advisor? I believe. Well, in any event, he was in the room, and it also got out of control in a similar way. Von Neumann was very quick and was starting to answer open problems, not answer them as much as, oh, here's an idea, I've just thought of. And apparently the last question was, who is your tailor? Which apparently ended the oral exam, and they all went to have, I guess they didn't have donuts, whatever they had in those days. So that was very cool and fun to have Avi obviously take such an exam. He also led to a rule at Princeton, which I don't know if it's still around. I had a chance to see some people. Didn't really ask them about this. And this one's meant to more embarrass. But they must be able to write, but not write English, which he does really well, but be able to write a hello world program. Because it wasn't completely clear. This had nothing to do with his passing the oral or not. But some of my colleagues said, can he actually write programs? And I said, he can do anything he wants, I'm sure. But maybe he would need an hour to look at the, in those days, the C manual to get somewhere. I don't think I had pushed on this. So actually Princeton, at least at the time, and maybe it went away, but introduced a programming requirement for graduate students where it wasn't tied to the oral and the written exams, but you actually had to write a program of some substance and submit it to some committee and prove you could actually write probably even more than hello world. Although, I don't know if that's really important. Although I think we see this more and more, this would be a whole different discussion I'd love to have with you. But we do see programming really playing a bigger and bigger role, I think, in what we do. And I'm not just talking about proofs like four-color or Kepler or other problems where they're actually only known mechanical proofs, but discovery of proofs, checking special cases before you actually go and try to prove something is often very powerful. I think Ron Graham's conjecture about Diophantine triples, squares, essentially Ramsey-type theorem was resolved, I think, well, it was published this year, and they did a gigantic satisfaction search to actually show that it was true. So, we see those things coming. But anyway, okay. I want to say something about Avi's talk. First of all, I know this talk. It's really hard to follow someone that's such a terrific speaker. I was a little nervous about that. I wish I could use your trick and have Avi come up now and take over, because Avi gives incredibly good talks, and there's nothing, I think some of the best I've ever seen. I did want to maybe bring him back to the style he used to use, and it was something like this. He loved to move down. I see a very mild laughter. I think lots of you haven't probably seen projector talks where we had this old piece of cardboard we moved down, I think, to hide the next punchline or the next, so people wouldn't read the proof ahead of your theorem statement or things like that. So that was my attempt to do that. And of course, that's part of the last proof. Okay. I've got some more things, and then I want to present, not so much new, but something that you might be interested in. I'd like to talk about the P and NP just at a high level. We've talked about it on and off forever. Some of you read my blog. I think there are lots of possibilities, and I think the community, I don't know if I can ask for a show of hands or anything, but I think a lot of people would probably believe they're not equal. I keep pointing out all kinds of different possibilities. I think Russell has done a really good job on that. I mean, it's just lots of strange possibilities that could happen. I was giving a talk at Stanford this summer, and I think I got asked at the end of the talk, what did I believe about P and NP? And Knuth was there, and I said, well, let's defer to Knuth, figuring I was safe, and no one's going to get mad when he says. And he at least I knew his answer. Actually, it's sort of like a lawyer. You should never ask a witness a question you don't know the answer to, right? I was pretty sure what he was going to say, and he said he really thought they probably were equal, but the algorithm and or the proof of the algorithm's correctness would never be. Never is too strong. I don't know if he said that, but would be immensely hard. And you can imagine that. You can imagine an algorithm that's actually maybe not all that complicated that we just can't prove correct. We have lots of examples already, I think, in computer science of very relatively simple algorithms whose proofs are quite long and difficult, certainly, right? We already have that, certainly crypto protocols that take long proofs, even regular algorithms, so we already see that. So he and I have argued about this. Avi's worked on so many things. He worked on, or still works on, lower bounds, and I think more than once, I think 93 was when you were working on the fusion method with Karchmer, right, around that time. And I remember you came to Princeton and you gave a talk on it. I'm not going to explain that method. You could talk offline with Avi. Okay. And I assume we still haven't proved P not equal to P. I haven't heard that yet. But I remember it took several lectures by you and Karchmer for me to really, I could follow the talks and then the next day I go, what? It just was somehow subtle what you're really doing. And I finally got it, I think after 3 talks it took me to really feel comfortable with. And it seemed really like a clever idea. But I remember at the time talking to you about it, and your comment was, I said, I just still don't know if it's going to solve the problem. And I think I should have made a bet, but you said something like, give me a year or 2. So, maybe you need 1994 and 2017, and maybe by your 70th birthday you resolve this. I don't know. I'd love to be here for that. But it just, of course, is really hard to prove general lower bounds. I think you guys will agree to that. And I think the thing that got us so excited, including especially your work, was that it applied so beautifully to things like monotone and other cases. Really it was beautiful, but it just didn't seem to be able to solve the general problem. And at some point you may want to start guessing you've guessed wrong. I know I was, I don't know, I'll just say, whenever I bring this up, I get sort of heated comments from colleagues that it can't possibly be true. Anyway, we can talk about that offline or at the end. Anyway. Where am I? Yeah. Avi once said, I'm going to kind of beat on this a little bit because it's, I think, fun, is all you, me, all I know is the Chinese remainder theorem. Now, that's right. I think I've actually used it a lot in several kind of, I think, fun papers. I think it's a good theorem. It's one that we do like and have used. And of course, there are beautiful improvements to the Chinese remainder theorem with errors and the like. But I'd like to bring up how this comment happened because I think it was an interesting, again, I'm trying to be a little different from the other talks. I hope that's okay. In my class, I sometimes ask, is this okay? Should I do something else? And here you have no choice. So, since I prepared the slides. In my class, I work at the chalk, so I could do something else. But I'm going to stick with this. Okay, so what happened is Nelson, the math department at the time when, he had a draft quite a while ago, that he was not circulating, but Andy Yao was still here at Princeton. I was here. And Yao had gotten a copy of a proof that they were not equal. And it was a very interesting thing. Yao was going to look through it, and Andy and I got together and said, well, let's look to it together and maybe have a little small group look at it. Avi was in town. I think at the time you weren't here yet permanently. And, you know, before we knew it, it wasn't quite this large a crowd, but we had a pretty good conference room filled with people, including Ed, who was gracious enough to, you know, help us try to understand what he had done. And of course, he's a terrific mathematician. I think he works in another area mostly, not complexity theory, and has done beautiful work. But you know, it's always a danger when maybe you move into another area, you don't understand some things. So in any event, I mean, I just have to add this. There's a Princeton folk story about the Poincare conjecture when it was still open for low dimensions, that a great topologist came to the math department and was going to outline their proof, and they started the lecture. And I think the first, I don't know, obviously not slides, but their first words were, well, everyone knows that the low dimension Poincare is equivalent to the following assertion. And I think I know who it was, but let's just say the host stood up and said, that's not true, time for tea. And that was the end of that talk. So it wasn't equivalent to that. It turned out, as we were going through the proof in front of the group, we very quickly discovered we needed just plain old integer multiplication. Nelson needed it to be in linear time to make some induction work. Because if that was linear time, then something else was linear time. And eventually he'd get this cascade of things that ran too fast, and then by a diagonalization argument, he would get the p not equal np. I mean, the structure of the proof wasn't completely unreasonable. Of course, even then, I mean, even today, it's n log n. I guess the t of n is just a little faster than log star, or something like that. But we might conjecture integer multiplication is really fast, but we don't know. I guess Martin and others have worked on that. So we turned to Ed and we said, well, how does that step go? And he said, I don't remember, or maybe he thought that was an obvious step. So on the fly, we started to figure this out, and Avi and I were, I think, up in the front, and I'm not trying to take credit for anything, but at one point I said, oh, I see, we'll use Chinese remainder theorem, the only thing I know. And it turns out you change the problem to a checking problem. In other words, you have x, you guess y, z, you have x and y, and you check it for lots of primes, and it's still not linear. But you've got alternation, it turns out, in what he was doing, and you could get the following result, that you could multiply on Turing machines with a fixed number of alternations. And this is when I think Avi said, this is just what you know. We later talked about it years later, and he said, no, I never said that. And I thought it was fun. I mean, I wasn't particularly upset. But luckily, I had a witness who's now at Georgia Tech, Dana Randall. A lot of you know Dana's work on different area, of course. But Dana at the time was, I think, visiting Dymax, and she said, yes, Avi, you said exactly that. So I have some collaboration. I really don't mind. It's a good theorem. I don't know if you can prove everything with it. Okay. I probably could go on with some other stories. I think I have, about 15 minutes. So let me just say something that's sort of related to this particular result, but is an old conjecture. And it's some work I did with Ken Regan in our Gödel's Lost Letter, our blog. Hopefully some of you read it. We get $1 for every reader every day. No, it doesn't quite work that way. Anyway, I wish. It's not relative to this talk, but a lot of you know the notation P/poly. that Dick Harp's in the audience. It was a joint paper, but Dick really invented it. But I think if we had trademarked it, Dick, and he got 50 cents or even a nickel every time that notation is used, you know, we could retire soon, you know. Well, we are going to retire soon. Okay. And the reason I bring this up, it's related a little bit to what we just talked about, multiplication. So I won't belabor this. Everyone knows, you know, the rational numbers, the algebraic numbers, the transcendental numbers. There was a nice question about Nogu's last talk. Is that constant? It's in one of these classes. Who knows what happens? So also, I think I'll zip through this. I mean, everyone knows these things. Maybe one thing about Cantor, though, and I'll skip that. But one thing about Cantor's theorem, well, first of all, there are a lot of curious facts. You probably all have seen tricks like this, but I just love this one. I mean, we know that pi and e are transcendental, but we don't know if their sum or the difference is transcendental, right? But we know one must be, because if they both were algebraic, then their sum would be algebraic. And you've all seen this trick or variations to it. It really is a very annoying problem. But I'll talk about a different annoying problem. But these are sort of the kinds of problems I wanted to say that we sometimes talk at the problem seminar. I just wanted to make one thing that's fun with the blog is I do look a lot at history of mathematics. And I don't know if everybody knows this. I mean, I'm sure everyone who, perhaps everyone in the room knows the famous diagonalization proof that the real numbers are not countable, or you've seen different versions of that. I don't know if you know, I won't go through it to save a little time, but that Cantor didn't do the diagonal proof. I think there's about a 14-year gap between proving that the real numbers were not countable by this, well, I can talk about it very quickly, this construction, and then he found the diagonal proof. And I've actually given this in class. I'm not sure students like it better or worse. And for those of you who teach this kind of stuff, I find of all the theorems that you ever teach to discrete math students, for some reason, and we have about 7 posts on this, people just don't believe Cantor's proof. Now, I forget who said it, but there's a quote by a very famous logician who said, "Why is such a little proof get so much static? You know, why does such a little simple proof have so many people disbelieving it or yelling at it? You know, kind of. It's not long and complicated, if you know it, right? But somehow there's something about diagonalization that's very subtle and obviously important to understand. But what Cantor did initially is he just said, suppose just say all the real numbers were constructive. He built an interval, and what he did is he took each number and made sure it wasn't in the interval. If he had to shrink it, that was fine. And as it shrunk, it still stayed a real interval. So he always had room. You know, your number might fall outside the interval, which was great, or it might fall in the middle, in which case he moved over appropriately. And and here's, of course, where you use the fact that it's really the real numbers. This interval is a nested interval, so by, Weierstrass, by the properties of the completeness of the real numbers, you have a nested set of intervals that converge to at least a number, either an interval or a number, and that number is not in the list by construction. So that's how he found it first. And I don't know of any way to use this construction to handle the general case. I don't know if people have done that. Maybe they have. Okay. But let's talk about some special numbers. So you may or may not all know about Louiville numbers. You know, if this was usual mathematics, that would be due to, Euler, because you know how things get named. There's at least a 50-50 chance if there's a name on something, it was discovered by someone else. That's just the way we work. But you notice this number has these huge gaps, and it converges too fast. So you can prove by a variety of methods, eventually Roth's theorem, but you can use other methods to prove this number is transcendental. It just converges too fast. So what does this have to do with computer science? Well, Juris Hartmanis and Richard Stearns in '65, I tried to get something when you were born. So you were 9, so you're probably not quite familiar yet with transcendental numbers, although I don't know, maybe. But they made the following interesting conjecture. They said, look, if you have a Turing machine, and instead of thinking of it as an accepting device, if you think of it as a generation device, which is actually what Turing looked at and so forth, but you just imagine that it's going to go on forever and just keep generating bits. They noticed that, very simple, if the number was a rational number, they're periodic, so you don't need a lot of computational power. If your number is the third, you just keep saying 3, 3, 3, 3. If it's 17 over 31, you say whatever. It's periodic. And if the number is the Louiville number, for example, you just say 1 and then count up to you run a counter, and when it gets big enough, you say 1 again. And in the meantime, you keep saying zeros. So as long as that gap is big enough, you have plenty of time to compute it, and you shoot it out. So transcendental numbers, at least the Louiville, and other numbers were computed by Turing machines. So they made the bold conjecture that, that you can't do anything else. So this would be, in some sense, it would be a very cool theorem, because it would be, I think, a new way to prove numbers aren't algebraic. Maybe, I think Noga was asked, his constants, are they algebraic, are they not? I think those are very difficult questions to ask, or right, to resolve. I'm not saying this would resolve them, but what's interesting is they asked if a number, I probably should underline this, but they call the number real time if there's a Turing machine that generates, say, bits of x roughly every k steps. So the critical thing is you can actually ask that you write a number every step, and you can prove, you'll see in a second, you can actually allow a little bit of a gap between when you write the numbers and it's still real time by some alphabet tricks. But it has to be constant. It can't be average constant or amortized. It has to be constant time. So you have to be able to generate the bits really fast. So their conjecture was if you had such a number, it was going to be not algebraic. Like square root 2 couldn't be generated this way. We don't know this. I mean, lots of things we don't know. So here's some simple observations we at least put in our post. We've not written a paper, but maybe we should. But I thought these were two kind of interesting things. So one is that if Hartmanis-Stearns' conjecture is true, then multiplication would be nonlinear. So I'll give you an idea of that in a second. Maybe you see it, obviously. But, I mean, that's bad news, right? Because if you have theorems generically of the form, if this is true, then there's a lower bound. That's nonlinear. And I'm talking about general Turing machine lower bounds, not special constant depth, not monotone, not some restriction on the model of computation, all right? So these are very hard. The other thing it would apply is something we know. So we do know that non-deterministic time is more powerful than deterministic time, but that's a sort of hard theorem. I mean, that's the famous work. I won't list all the authors, but that's the famous work that generalized the Pebbling method with segregators. I mean, that's a hard theorem. I'm not saying this proof would be easier because the Hartmanis-Stearns conjecture might be very hard to prove, but if you could, you would get this. And I decided not to include it, just I think partly for time. There's a paper that's actually just about 2 years old by Freivalds, where he didn't observe this, but he had some ideas how to prove the Hartmann-Stern's conjecture was true based on some Diophantine analysis he had been working on. But it was all, if you could prove this, then this would be true. And I think, especially the first theorem B says, I don't think so. It's going to be tough. And the point is, and this goes back, I assume Avi would agree, or others in the audience who thought about lower bounds for general models of Turing machines. We just don't know how to prove that, right? I mean, you probably all know this. I've been involved with this. We tried to prove lower bounds for just satisfaction and tried to get, say, superlinear lower bounds. Couldn't do that. The best we could get, I think Ryan Williams, improved the work that Lance Fortnow and Dieter and I did showed that even if you add restrictions to the Turing machines, you couldn't really get very good bounds. So here we are saying we're all real sure P doesn't equal NP, but we can't even prove that satisfaction can be done at linear time on a Turing machine. I mean, I find that somewhat difficult. So I think this is sort of, at least to me, evidence that this conjecture is going to be hard. But let me just tell you how this kind of works, and it's a standard trick. So the trick we're talking about, I'll just call the overlap trick. So the following is, suppose multiplication really was linear. Then you really just have two computations going on at once. You can think of them as Alice and Bob back again. And what one of them is doing, say, Alice, is she's already computed the first n bits of the number that you need. And luckily, Brent and work that he did a long time ago shows that just about, I think, just about all algebraic numbers can be computed essentially in multiplication time. You compute a lot of bits, like the first n bits in multiplication, which is not a trivial theorem. So she's already computed the first n bits using Brent and the magic multiplier. So she's just reading them off. And Bob's trying to do the same for a much bigger stretch of bits. But notice they can take turns, or you can run them at the same time. If you like, Turing machines can do that. And when Alice is just done, Bob can arrange it to have his head just right here and start pumping out his bits. And then Alice jumps to, say, 16 times larger. And there's nothing magic about 4. It's just to make some recursions actually work. So the idea is you completely start from the beginning each cycle and recompute, but because of linearity, it will work out that when the first player has run out of bits to write out in real time, the second player is ready to help and to write out bits, the next bits in real time. It's not a particularly new trick. And I think, I'll say after we did this, there's actually some old work due to Fisher, Meyer, and Rosenberg that really says the same thing, and actually we didn't know about it when we were first working on it, so it's doing the same thing. And I think my time is about up, so let me just say, I couldn't find that really cool cake, so I found this. I wanted to say Avi, but it just didn't quite work. And I think this is really true. Avi is a great problem solver. You've solved so many wonderful problems, but I think you've also created whole chunks of fields from the theoretical computer community. And we really want to wish you a happy birthday and like you to continue to solve really hard problems and create whole new areas. And we thank you for that. Thank you very much.